It gets so cold that the atmosphere itself might freeze out.
Freeze out like the air turns to ice.
Yeah, the carbon dioxide and nitrogen could actually condense into snow and fall to the ground, leaving a pure vacuum behind.
That is a terrifying visual. A boiling furnace on one side, a frozen vacuum on the other. But wait, what about the middle, where the light meets the dark?
Ah, you're talking about the Terminator line, the ring of permanent twilight.
Yeah, could something live there?
Climatologists run some really complex models on this. If the planet has a thick enough atmosphere to transport heat from the day side to the night side via heavy winds, there might be a narrow band along that Terminator line where the temperatures moderate just enough.
So you could theoretically have life clinging to this perpetual twilight zone with a frozen wasteland on one horizon and a burning desert on the other.
It's a fascinating theoretical refuge, for sure. But even if life found a foothold there, it has to survive the second half of the red dwarf Catch-22. And this one is far more destructive.
Oh no, what is it?
Red dwarfs are notoriously volatile.
Volatile how? Because they're so small, shouldn't they be kind of quiet?
You'd think so, but their internal structure is totally different from our sun's. Red dwarfs are fully convective.
What does that mean exactly?
It means the boiling plasma inside them churns all the way from the very core straight up to the surface. This creates incredibly powerful twisted magnetic fields, and when those magnetic field lines snap and reconnect, they release a stellar flare.
We get solar flares from our sun though, right? Sometimes they mess with our satellites, but we survive.
We survive because our sun is relatively calm, and importantly, we are sitting 93 million miles away.
Ah. And the red dwarf planet is huddled right up against the glass.
Exactly. A planet orbiting a red dwarf is sitting right in the blast zone. When a red dwarf flares, it unleashes a torrent of high-energy ultraviolet and X-ray radiation. Because the planet is so close, it gets hit with the full force of these eruptions constantly.
So what does a blast of X-rays actually do to a planet?
It triggers a process called atmospheric stripping. The high-energy radiation smashes directly into the molecules of the planet's atmosphere. It literally splits water molecules apart into hydrogen and oxygen.
And then what?
The lighter hydrogen is energized so much by the radiation that it escapes the planet's gravity completely. Over billions of years, the red dwarf will literally sandblast the entire atmosphere and ocean off the planet, venting it into deep space.
Wow. And without an atmosphere, liquid water boils off or freezes instantly, so the habitability is completely gone.
Not to mention the surface is continuously bathed in lethal radiation that shatters the complex organic molecules required for biology anyway.
So 75% of the stars in the universe offer infinite time, but absolutely terrible living conditions. They freeze half the planet, bake the other half, and blast away the atmosphere. It really makes you realize that just being at the right distance, just standing in the Goldilocks ring, is absolutely no guarantee of safety.
No, it is merely a prerequisite. The stellar habitable zone just provides the potential for liquid water. But the star is really only half the equation.
Which brings us perfectly to layer 2, planetary habitability. Because if the star is the campfire setting the stage, the planet itself has to be an active participant.
This is a major pivot in how we need to understand the universe. We have to stop thinking like astronomers who just measure orbital distances and start thinking like geologists and atmospheric chemists.
We have to look at the rock itself.
Exactly. A planet isn't a passive billiard ball just sitting near a fire. It is a wildly dynamic, active system. To unlock the potential of the stellar habitable zone, the planet basically has to build and maintain its own shield and thermostat.
And I think the best way to really grasp this is to look at the spectacular failures. We don't even have to leave our own solar system to find them. We have 2 cautionary tales right next door that technically grazed the habitable zone, but completely failed the planetary test.
Venus and Mars, the tragic siblings of Earth.
Let's start with Venus, the inner edge of the zone. If you just look at the raw stats on paper, Venus looks like a slam dunk for life.
It is often called Earth's twin for a very good reason. Venus is almost identically matched in size, mass, and rocky composition to Earth. It sits just on the inner edge of our sun's habitable zone.
And didn't it used to be more Earth-like?
Yes. Many planetary scientists believe that billions of years ago, Venus looked a lot like Earth, potentially with shallow liquid water oceans and a moderate climate.
So what in the world happened? Because Venus today is a literal nightmare.
Venus suffered a catastrophic breakdown of its atmospheric thermostat. It experienced a runaway greenhouse effect. Remember how we said that being a little too close to the star causes water to boil?
Yes, the furnace room.
As the young sun gradually grew brighter over millions of years, Venus warmed up. its oceans began to evaporate. Now, water vapor is actually a very potent greenhouse gas.
So the air got thicker with steam.
Right. So as more water evaporated into the air, the atmosphere trapped more heat from the sun. That increased heat caused even more ocean water to evaporate, which trapped more heat.
It's a vicious, unstoppable feedback loop.
Until the oceans were entirely gone, basically boiled into the sky. And once the water was high in the upper atmosphere, the sun's ultraviolet light broke the water molecules apart.
Just like the red dwarf flares.
Exactly the same principle. The hydrogen escaped into space, and the oxygen bonded with carbon to form carbon dioxide.
So the water was just permanently deleted from the planet?
And that triggered the second massive disaster. On Earth, liquid oceans are crucial for trapping carbon. They dissolve carbon dioxide out of the air and lock it away in rocks.
But Venus had no oceans left.
Right. Without liquid oceans, Venus lost its massive carbon sink. But volcanoes kept erupting, pumping massive amounts of carbon dioxide into the sky, and there was absolutely no water to wash it out.
So it just piled up.
In and up.
It accumulated over billions of years. Today, the atmosphere of Venus is 90 times thicker than Earth's. It is a crushing, suffocating blanket of almost pure carbon dioxide.
90 times.
If you stood on the surface, the atmospheric pressure would be like being a mile underwater on Earth. You would be instantly crushed.
Crushed and then roasted, right.
Because that massive CO2 blanket is incredibly efficient at trapping infrared heat, the surface temperature on Venus is a constant 460 degrees Celsius.
Wow.
That is hot enough to melt lead. It would vaporize any organic material instantly.
So Venus is the tragedy of a planet that got slightly too warm, lost control of its gases, and literally choked itself to death.
Yeah.
Now let's swing to the outer edge of the zone and look at Mars.
Mars is the opposite kind of tragedy. It didn't choke on a thick atmosphere, it just withered away. Mars technically sits on the outer edge of the habitable zone, and we know for a fact it used to have liquid water, right? The rovers are constantly sending back pictures of dried up river deltas and ancient lake beds.
Exactly. Mars was once a wet, dynamic world with a thick atmosphere. But Mars had a fatal structural flaw compared to Earth and Venus: its size. Mars only has about 10% of Earth's mass.
Why does the physical size of the rock matter if it's sitting at a decent distance from the sun? I mean, we live on the surface, not deep in the rock.
It matters immensely because of internal heat. When a planet forms, it is a molten ball of magma, and over billions of years it cools down. Because Mars is so small, its surface area to volume ratio meant it radiated its internal heat into space much, much faster than Earth did.
Like a small cup of coffee going cold way faster than a massive insulated thermos.
That's a perfect way to look at it. And when the deep interior of Mars cooled down, a critical mechanism shut off. Deep inside a rocky planet, you usually have a core of liquid iron. If the planet is hot enough, that liquid iron undergoes convection, it churns and boils.
And that churning metal generates a magnetic field, right?
It creates a massive geodynamo. Earth's churning core projects an invisible magnetic force field thousands of miles out into space. It acts as an active deflector shield against the solar wind.
Which is the radiation from the sun.
Right, a constant violent stream of high-energy charged particles blowing off the sun.
So when Mars cooled down like that small cup of coffee?
Its liquid core stopped churning. The geodynamo completely died, and the planetary magnetic shield dropped.
Leaving the planet totally exposed to the solar wind.
Completely defenseless. Over hundreds of millions of years, those high-energy particles from the sun slammed directly into the Martian atmosphere. They physically knocked the air molecules out into space in a process called sputtering.
Just chipping it away.
It was exactly like sandblasting a painting off a wall, molecule by molecule.
And once the atmosphere was sandblasted away, the planet couldn't hold on to its heat anymore.
Right. The atmospheric pressure dropped so low that the liquid water either froze into the ice caps or sublimated directly into vapor and was blown away too. Today, Mars is a frozen, irradiated desert with an atmosphere 100 times thinner than Earth's.
So a planet is basically an active spacecraft. It has to generate its own deflector shields, the magnetic field, to protect its crew from space weather, and it has to manage its own life support systems, a stable atmosphere so the ship doesn't overheat.
Yes.
If the deflector shields fail like on Mars, or the life support system spirals out of control like on Venus, it doesn't matter how close you are to the campfire, the crew is dead.
That spacecraft analogy is spot on. Habitability requires massive internal geological power.
That honestly makes me look at Earth entirely differently. We have the hot churning core, so our magnetic shield is up. But how have we avoided Venus's fate? How has Earth kept its life support system perfectly balanced for 4 billion years without overheating or freezing?
It is arguably the most elegant mechanism in all of planetary science. Earth possesses a built-in geological thermostat. It's called the carbonate-silicate cycle. The carbonate-silicate cycle. Okay, I need to understand this. How does a rock cycle act as a thermostat for the air?
It is a vast, self-correcting feedback loop that intimately connects the atmosphere, the oceans, and the deep Earth. Let's say the Earth starts getting a little too hot. Perhaps massive volcanic activity has released too much CO2, or the sun gets a bit brighter.
Okay, so the global temperature starts to rise.
As the planet warms, more water evaporates from the oceans, which naturally increases global rainfall. Now, as that heavy rain falls through the atmosphere, the water chemically reacts with the carbon dioxide in the air, creating a very mild carbonic acid.
Wait, so the rain literally absorbs the greenhouse gases out of the sky as it falls?
Exactly. It scrubs the air. When that slightly acidic rain hits the mountains and rocks, it causes chemical weathering. It physically breaks down the silicate rocks, and the carbon is washed down the rivers and into the oceans as bicarbonate ions. So the carbon has officially moved from the sky to the ocean.
And in the ocean, marine life like microscopic plankton and coral uses those bicarbonate ions, along with calcium, to build their shells.
That's incredible.
And when those organisms die, they sink to the bottom of the ocean and compress into massive layers of limestone and carbonate rocks. The carbon is now securely locked away in the Earth's solid crust.
That is brilliant. The hotter it gets, the more it rains. The more it rains, the more carbon is scrubbed from the sky and locked into rocks at the bottom of the sea. So the greenhouse effect weakens and the planet naturally cools back down.
It entirely self-corrects. But the beauty is, the cycle works in the other direction too. What if a massive ice age begins?
Well, if the planet freezes over, the oceans ice up and the rain stops.
And if the rain stops, the process of scrubbing carbon out of the atmosphere completely halts.